What effect does color have in light? Here's an example of some M&Ms under a blue light. Here's an example of some M&Ms under the white light. How do they look different under the blue light? How do they look different under the red light? Now this red light is so extreme it's messing the camera up too, but we're still getting a color shift. How do they look different under the green light? To get a better feel for, or a better understanding of why objects look different under different colors of light, we need to go back and look at what light is and how we see light and what color is in an object. So let's look at what is light. Sometimes light is described as a particle, sometimes light is described as a wave. In this class we'll talk about it as a wave and define light as the very narrow portion of the electromagnetic spectrum that is visible to the human eye. This is a chart, a picture, that shows the electromagnetic spectrum, and you can see that in the middle of the electromagnetic spectrum is the visible spectrum. So right here. Electromagnetic spectrum is waves that are measured in nanometers. So we can see down here at 300 nanometers, we're looking at ultraviolet, which we don't really see. If we go lower than that, we have X-rays and gamma rays and cosmic rays. Over here on the other end, where we have 1,000 nanometers, we're into infrared heat, and then microwaves and TV waves, radio waves. Those are much larger waves, and we don't see those as well. So this is kind of the range that we see as the visible spectrum. So this is the range of light that we see. You'll also notice that this example of the visible spectrum is broken into different color bands. So different wavelengths, like for example this 400 nanometer wavelength, are perceived by our eyes or are perceived by our brains, interpreted by our brains to be specific colors. So 400 down here in this kind of magenta range, we're up here at 500 and we're kind of in between blue and green. We get to 600 and we're kind of got some yellow transitioning into orange, and here at 700 we're pretty squarely into red. So each of those different wavelengths in those different frequencies and nanometers are interpreted by as different colors by our brain. When sunlight is refracted by a prism, each discrete wavelength can be seen. This is something that Isaac Newton figured out. Sunlight is considered a full spectrum light source because it really contains all of the visible spectrum of color. These same colors were what we saw in that chart of the visible spectrum. This is an example of the color wheel of light. Notice it's a little different than the color wheel that we're used to in pigment. So our primary colors in light are red, green, and blue, and our secondary colors are yellow, cyan, and magenta. Also notice that at the center of this circle, we have white light. And what that's telling us is that if we added a red light plus a green light plus a blue light, the three of them together would create white light. And you can also think of the reverse of that. When we see white light, we are actually seeing a light that is a combination or contains all of these different colors. So you can take that white light, and if we go back to that slide of the prism, you can take that white light and you can split out all those different colors from that white light. You can also create white light by mixing the complementary colors of light. So yellow plus blue equals white, red plus cyan equals white, green plus magenta equals white. Here's some other qualities of light that are useful and have an impact on what we see and are useful to lighting designers to be able to understand, or designers in general to understand. Light travels in straight lines unless modified. The results of that is that we can get a shadow. If you put your hand out in front of a light source, it creates a shadow, or it blocks the light. Because the light is traveling in a straight line, it hits that hand and is not able to go around it. You also, because of that light traveling in a straight line, that allows you to be able to focus the rays of light with like a magnifying glass or a lens. You can focus and intensify that light. Light waves pass through one another without changing each other. This is helpful because if I have a whole bunch of lights that I'm creating a light plot with or a lighting design with, oftentimes those beams of light pass through one another. And as they're on their way to the object that I'm shining that light on, but those beams of light passing through one another don't have any effect on each other. They just don't change. And then light is invisible unless a medium such as dust or mist scatters it in the direction of the eye. So the fact is you are not seeing light. If you look straight in front of you, you can't see the light. If you stick your hand out in front of you, you can see the light on your hand. But if you pull your hand back away, there's nothing there. You're just not seeing the light. The light is there, but we don't see it unless it is actually bouncing off of a surface. And then what we're really seeing is the surface. So if you want to be able to see a beam of light in the air, you actually have to add some sort of particles like smoke or water mist. And then what you're actually seeing is the little particles. But those particles help you to see then the beam of light. And so that's something that we do in lighting design, is put haze or fog or smoke or water mist into the air so that we can see the beams of light. All right, so we talked just briefly about what light is, and now we're going to talk about what is color in an object, or what gives an object color. And really, color is a function of the chemical makeup of an object. And to make different colored paints, chemists look for materials that look like a particular color to use as pigments. They mix the pigments together with other materials to create, for example, a blue paint. Every object that we have has a certain amount of essentially pigment that's created by the chemical makeup of that object. My computer is sitting on a wooden desk, and the chemical makeup of that wood has a particular color, and I'm sure there's also a stain, and the chemical makeup of the stain that's been applied to the wood has also added color to the wood. Here's the color wheel in pigment. You're already very familiar with this, I assume, with your primary colors of red, blue, and yellow, different from the primary colors of light, red, blue, and green. And then, of course, your secondary colors, violet, green, and orange. Notice that the primary colors of light and pigment, we know that they're different. Also notice that when the primary colors of pigment are mixed, the result is a dark color close to black. Why do you think that is? Well, to figure that out, we need to make sure that we understand how we see color. So here's an image of how we see color. There's the sunlight, and that fact that sunlight is a full spectrum light source is represented by the rainbow. We would see those kind of rays of light coming from the sun as white, but they actually contain all of those colors. When that ray of light from the sun strikes the apple with the red pigment, the apple absorbs the wavelengths for all of the colors other than red. The red pigment in the apple reflects the red wavelength off to our eyes. So the other colors are being absorbed, but the red apple has red pigment, so it is reflecting the red wavelength to our eyes. Our eyes are getting that red wavelength. They're not getting the other wavelengths. Those are staying at the apple. When the reflected light enters our eyes, it stimulates two types of receptors. You've heard this before. Rods are sensitive to light and dark. Cones are sensitive to color. And the three types of cones are sensitive to red, green, and blue. You should notice that red, green, and blue are the primary colors of light. There is likely those two are, I'm sure, correlated together. One of the kind of unique things about this process is that your brain decides on the color. When the reflected light enters your eyes, it stimulates two types of receptors. The receptors send signals to our brains to process. Our brains receive the signals from our eyes and decide what the signals mean. Our brains learn that a particular combination of signals equals red. And some of the unique things about that, one of the unique things about that is that means that because colors is a learned response to stimuli, each of us can be receiving the same stimuli, and we can actually perceive it slightly differently based on how we learned to quantify the stimuli. And in certain languages and different cultures, they actually use, they have more or less words for color than we do, for different colors than we do in English. And so really that, while there's similarities, that just shows us how different, how much color is a construct of our brains and of how society has learned or decided to quantify the stimuli that our eyes are sending to our brains. All right, so then this chart expands on this idea. So we have white light sources that are shining on multiple different colors. We have a white light source composed of all of the different colors. We see it as the three primaries, red, green, and blue. Shines on a red object, it absorbs the blue and the green, and it reflects the red. On a green object, it absorbs the blue and the red and reflects the green. On a blue object, it absorbs the red and the green and reflects the blue. When we get to a white object, it's actually reflecting all the red, green, and blue. It's reflecting white back to us. And if we get to the black object, we have all of the colors absorbed. And if we look at that, that should seem somewhat self-explanatory. We perceive an object as white because it's reflecting all of the pigments to us. With all of the pigments reflected to our eyes, that is white light. Red, green, and blue together is the white light. So we're perceiving as white. And when something that we perceive as black is absorbing all of the colors of the light, there's no light that is reflecting back to our eyes. Consequently, we say this is black. There's no light reflecting back to our eyes. And if we look at the color wheels again and compare them, we can understand a little bit more about the differences between these two color wheels. The color wheel of light includes all of the visible spectrum of light. So it's got the red, the blue, the green, and all the secondary colors. That's all of it together in that white light. So that's what that color wheel of light is made up of, is all of the visible spectrum of the colors in light. The color wheel of pigment is a little bit different, and what we are really seeing is the colors of white light reflected off of pigment to our eyes. And that's why when we take kind of all of the pigment colors and put them together, the idea here is it's kind of absorbing all of the light and nothing is reflecting back to our eyes. So white is all of the light reflected and black is all of that light absorbed.